Hello everyone. Let me ask you a very simple question. What happens to objects that fall under gravity? Well, a very simple answer would be to say that it attains a constant acceleration due to the acceleration due to gravity, and its velocity increases at a constant rate with respect to time. However, in real life scenarios, this does not usually happen like that. The velocities of falling objects, they usually obtain an upper limit when they are falling through the air or some other kind of a medium. This upper limit, this constant value that the velocities reach beyond which they cannot go, they are known as terminal velocities or terminal speeds. Now, the reason this real life scenario is different from the ideal case scenario of constant acceleration is because in real life scenarios, objects are usually falling in the presence of some kind of an external medium. And the presence of an external medium introduces what is known as a drag force. And the beautiful relationship of the drag force and the gravitational attraction creates a very interesting pattern as to how the velocity of the falling object is going to change with respect to time. And I can show you the relationship of this velocity of a falling object with time when it experiences some kind of a drag due to the presence of a medium by performing some very simple calculations. So let's suppose that there is some kind of a point mass that is falling through some kind of a medium and it has a mass of m, so it will be experiencing some kind of a force mg in the downward direction. And if this point mass is present in some kind of an external medium like air or some kind of a fluid, it is going to experience some kind of a drag force. Now, the nature of the drag force could depend upon various parameters like the size, shape of the object, the area of the cross section, the density of the medium, etc., etc. But the parameter that we are most interested in is the relationship of the drag force with the instantaneous velocity. Now, as it turns out, we can classify various falling objects through different medium in two different cases. In case number one, the drag force is directly proportional to the instantaneous velocity of the object. And in case number two, the drag force of the falling object is directly proportional to the square of the instantaneous velocity of the object. Now, case number one is usually seen in those situations where the object is falling through a medium that exhibits laminar flow. That means the particles of the medium, they follow these smooth trajectories around the falling object. While the case number two is usually seen for those kind of circumstances where an object is falling through a medium that exhibits what is known as turbulent flow, which is when the particles in the medium do not exhibit these kind of smooth trajectories, but rather you see these eddies and these turbulences in the nature of its motion. The case number two is usually for objects that are falling very fast through air or the atmosphere, while the case number one is usually for objects that are falling slowly through some kind of a medium like water, let's suppose. So let us look at the forces involved in case number one. That means if the drag force is directly proportional to the velocity, then let me write the constant of proportionality as, let's suppose, some kind of a term b. Now, usually when you study terminal velocity, this quantity that I've written here, b, may depend upon various factors. As I've just now said, it may depend upon the area of cross section of the objects, the size, the shape, the density of the medium, etc., etc. But I'm going to create this compact parameter b to include all of those quantities so that I am only interested in the nature of the relationship that it has with this particular quantity v. So if I can write the forces as both the weight acting downwards and as the drag force acting upwards and against the motion, then from the Newton's second law, I can write the nature of motion as whatever acceleration is experienced by this kind of an object that is falling down is the result of the net forces involved. Now, the net forces depends upon which direction I take as forward. So let's suppose I take a forward direction of downward as the positive x-axis. All right, so if I take a forward direction of downward as a positive axis, so let's suppose initially the object was here. So if the object was here initially at time t is equal to 0, let's suppose. So at time t is equal to 0, the object was here, it fell with 0 velocity. So the object was dropped at time t is equal to 0. And I take the downward displacement as the positive x-axis. In that case, in the forward direction, you have the force mg. In the backward direction, you have the force, the drag force minus bv is equal to m This can be simplified to mg minus bv is equal to m dv upon dt, where dv upon dt is nothing but the acceleration, the instantaneous acceleration. So this left hand side can then be written as mg minus bv upon m is equal to dv upon dt. Now I can apply separation of variables to solve this problem. So if I say that dt upon m is equal to dv upon mg minus bv, in that kind of a situation I can integrate both the left hand side and the right hand side from time t is equal to 0 to some random time t, and from velocity 0 to some random velocity v. So the left hand side in this kind of a situation is simply t upon m, while the right hand side, here I can use the simple integration formula that if you have an integration of the manner integration of dx divided by a plus bx, where a and b are constants, this is simply nothing but the constant 1 upon b ln of a plus bx. All right, so if I use this kind of a integration expression here, then this simply becomes, the constant here is minus b, so minus 1 upon b ln mg minus bv, and the limits are from 0 to v. This can be simplified to t is equal to minus m upon b ln mg minus bv in the first term, and in the second term if I put v is equal to 0, this simply gives me ln mg. This can be further simplified to, let's just do these calculations, minus m upon b, this simply becomes mg minus bv upon mg, which simply becomes bt upon m minus is equal to ln mg minus bv upon mg. Since this is a log that I have here, a natural log, I can take the exponential of the left hand side. In that situation, I'll have e to the power minus bt upon m is equal to mg minus bv upon mg, which can be further simplified to e to the power minus bt upon m is equal to 1 minus bv upon mg. So if I rearrange the terms, bv upon mg I bring to the left hand side, and this becomes 1 minus e to the power minus bt upon m. So finally I have an expression of the velocity here. So the expression of the velocity finally comes out to be velocity with respect to time is equal to mg upon b 1 minus e to the power minus bt upon m. This, as it turns out, is the actual relationship of velocity of the falling object with respect to time when the falling object is falling through some kind of a medium that introduces a drag force which is directly proportional to its instantaneous velocity. Now here the mass is a constant, g is the acceleration due to gravity, which is a constant, b depends upon the parameters, as I said, depends upon the situation, the size, the shape of the object, the density of the medium, etc. I'm just going to call it some kind of a constant of proportionality. So let me show the variation of this kind of a function with respect to time. So here I have this graph that gives us an idea about what is the nature of how the velocity changes with respect to time. So if you look at how the velocity of the object which changes, let's suppose the velocity is in the y-axis and the time is in the x-axis. So this is the time here and this is the velocity with respect to time. As you can see, the velocity is initially increasing, of course. Initially, the drag force is very less because the velocity itself is less. And since the drag force is directly proportional to the velocity, drag force is also less. So initially, the velocity keeps on increasing very fast, but after certain intervals of time, due to the drag force, the rate at which it increases starts decreasing. And as it turns out, what happens is that the velocity approaches a particular constant value, and this constant value which the velocity approaches is known as the terminal velocity. So the general expression for the velocity here is, of course, vt is equal to what we just obtained, mg upon v 1 minus e to the power minus bt upon m. But as time tends to infinity, that means as t becomes very, very large, in that kind of a situation, this term approaches infinity and this entire term approaches what? It approaches 0. In that kind of a situation, what do you get? The velocity comes out to be mg upon b. So as you can see, this velocity, which I am going to call as the terminal velocity, is actually mg upon b. This is the terminal velocity of the object as it is undergoing fall. Now, if my interest was just in obtaining the terminal velocity, I could have obtained it straight from the calculations. You see, terminal velocity happens when the drag force and the gravitational attraction actually balances each other out. When the drag force becomes equal to the gravitational attraction, that is when the terminal velocity arises. So when this particular quantity actually becomes zero, in that kind of a situation, from here I can obtain the terminal velocity, that if a is equal to 0, that means the acceleration becomes 0 because both the forces in the upward and in the downward directions are balanced. Then mg is simply equal to bv. Vt is the terminal velocity. So Vt here is nothing but mg upon b. So this is the terminal velocity which I have obtained from the general expression here. So this is the terminal velocity, and this is the general expression of the nature of the velocity dependence on time as the object is falling through some kind of a medium that exhibits a constant proportionality with velocity as the drag force. Now this was for case number 1. What if we perform the similar calculations for case number 2? So in case number 2, what happens is that there is a proportionality of v square. That means the drag force is directly proportional to the square of the velocity. Right. In that case also I can perform the similar calculations and see what kind of a situation I end up with. So in case number 2, where the drag force is directly proportional to the square of the velocity, and again the constant of proportionality I'm assuming to be b could depend upon various other parameters that I'm not considering right now because they depend on the size, the shape and the medium, etc. I'm only interested in the relationship that it has with the velocity term. So if the drag force is bv square, then the net forces will result in a particular acceleration that would be given as the weight minus bv square is equal to ma. So that's it. Our job is to perform these calculations. So ma, instead of ma, I can write dv upon dt. And using the separation of variables method, I can write here dt upon m is equal to dv upon mg minus bv square. So if I'm going to integrate it, then I'm going to integrate it when the object falls at time t is equal to 0, it has a velocity 0, and at some random time t, it has a velocity of v. I'm going to further simplify this as dt upon m integration from 0 to t is equal to, if I take the b out of this equation or the right hand side, this becomes dv upon mg upon b minus v square. From 0 to v. Now here again I can use a very standard integral expression, that if you have an integral of the form dx upon a square minus x square, where a is some kind of a constant, this is nothing but 1 upon 2a ln a plus x upon a minus x. So if I use this expression here, then what I can say is that instead of us having mg upon b, I can say that we have here a root over mg upon b square. Then this will replicate a square minus this x square term that I've written in the right hand side. So this is nothing but what? The left hand side is just t upon m. The right hand side is 1 upon b multiplied by 1 upon 2 multiplied by 1 upon from a here. The a here is root over mg upon b, and ln root over mg upon b plus v upon root over mg upon b minus v. Limits are from 0 to v. So let me simplify this. Just few more calculations left. If I take the constants to the right hand side, this is going to become 1 upon m into 2b into root over mg upon bt is equal to ln. In the bracket I can write this as root over mg plus v root over b, and here root over mg minus v root over b, and again the limits of 0 to v. This simply becomes, the first term is root over mg plus v root over b, the second term is root over mg minus v root over b minus ln. If v is equal to 0, I have root over mg here and root over mg here. So what is ln 1? So this term will automatically go to 0. ln is equal to 0. So finally I am left with 2 root over bg upon mt is equal to ln root over mg plus v root b and root over mg minus v root b. The expression may look complicated, but it's not that difficult if you follow the steps. Now again, I have a log here, the natural logarithm, right? If I take the exponential of the left hand side, what does this become? It simply becomes exponential to the power twice root over bg upon mt is equal to root over mg plus v root over b upon root over mg minus v root over b. Just a couple of steps more. I'm going to simplify this further. So here I can write mg root over mg e to the power twice root over bg upon mt minus v root over b e to the power twice root over bg upon mt is equal to root over mg plus v root over b. Okay, I'm trying to obtain some kind of a simplified expression. That is why I'm making all of these substitutions. And now if I again rearrange the whole things in such a manner that if I write root over mg e to the power twice root over bg upon mt, and if I bring this term to the left hand side, I simply get root over mg, and here I'll get v root over b plus v root over b e to the power twice root over bg upon mt. And again, I can finally write, if I take root over mg out of the two terms, e to the power twice root over bg upon mt minus 1, and here v root over b, if I take out 1 plus e to the power twice root over bg upon mt. Finally, let me write this in this manner that you may look like you are familiar with this expression. So if I write this here, and if I bring the further term, if I bring this term to the left hand side, it will have e to the power 2 root over bg upon m. Here I have a t plus 1 is equal to v root over b upon root over mg. Now here you can see that this left hand side expression may look familiar to you. You may know that expressions of the form, let's suppose exponential to the power twice x minus 1 divided by exponential to the power twice x plus 1 can be written as some other kind of a trigonometric function. It is actually equal to tan hyperbolic x. And if we use this expression, I can further simplify my results. So I can say that v root over b upon mg is equal to tan hyperbolic root over bg upon mt. And finally, we have the expression for the velocity of an object falling through a medium that introduces a drag, which is proportional to the square of the velocity. That is vt is equal to square root of mg upon b tan hyperbolic root over bg upon mt. Now again, I can show you a geometrical representation of how this particular expression varies with respect to time. So here I have a graphical representation of how the velocity is changing with respect to time for this kind of a mathematical function. Again, in the y-axis, I have the velocity, which is vt, and in the x-axis, I have the time here. So as you can see, compared to the previous graph, this approaches the constant terminal velocity very fast. You see, initially the velocity is increasing. However, because the drag force is proportional to the square of the instantaneous velocity, the drag force increases very, very fast. And because of this, the velocity also approaches a constant value very quickly. So this is the constant value of the terminal velocity. So the general relationship for the velocity is, of course, what we have just now obtained, mg upon b, and tan hyperbolic, you have root over bg upon mt. And of course, you know that if time is tending towards infinity for very large values of time, what happens to the tan hyperbolic function? The tan hyperbolic function very quickly tends towards plus 1. So in that kind of a scenario, the terminal velocity will be simply equal to root over mg upon b. So the terminal velocity vt will be equal to root over mg upon B. Now, a few points here. You may have done calculations where you may have written the complete expression for what I have written here as the parameter B. The parameter B is all the terms that are responsible for creating the constant of proportionality. It may depend upon the shape, size, density of the medium, shape, size of the object, etc., etc. If you have that kind of an expression, you can plug that here, and this will give you a more general expression for the terminal velocity. Otherwise, I'm just writing all of those parameters in this compact form of P. Second of all, if you look at the terminal velocity we obtained here, that was mg upon b. That's a larger number compared to the terminal velocity we have obtained here, which is square root of the mg upon b. So, which is kind of obvious, right? In the first case scenario, the drag force was directly proportional to the velocity. But in the second case scenario, the drag force is directly proportional to the square of the velocity. So in the second case, the drag force becomes very large very quickly, because of which the terminal velocity is achieved very quickly, and its magnitude, all else being equal, will be lesser. So this is the general expression for the velocity. But if you want to obtain terminal velocity, we could have easily obtained it earlier also. Like for example here, if I say that the acceleration experience is 0, in that kind of a situation, mg minus b, the terminal velocity square, will give us what the terminal velocity is. So mg is equal to b vt square, or vt is equal to mg upon b root over. So if I'm only interested in obtaining the terminal velocity, I can simply obtain it by making sure that both the forces, the gravitational force and the drag force, balance each other out. And from there I can obtain the terminal velocity. But here I have shown you a general situation of obtaining the relationship of the velocity with respect to time in both these cases, of when the drag force is, in the first case scenario, directly proportional to the velocity, and in the second case scenario, directly proportional to the square of the velocity. So this is how we can show how the actual velocities of falling objects do not increase at a constant rate, but rather approaches a constant value known as terminal velocity in a real scenario where they fall in some kind of an external medium. So that is all for today. I hope you learned something. See you in the next video. Thank you very much.